Good morning. I'm Margie O'Driscoll, and on behalf of the Center for Innovation's Board of Directors, I'd like to welcome you to today's webinar. The mission of the center is to catalyze innovation in the architecture, engineering, and construction industry for a better tomorrow for all people. So we thank you for joining us today. We'd like to take a moment to express our gratitude to the many sponsors who make our work possible. We would not be here today without your support. Thank you so much. CFI would be remiss not to share a little bit about our ongoing work with Ukrainian leaders as they rebuild during war and plan for comprehensive reconstruction. CFI has invited 12 Ukrainians to the San Francisco Bay Area next month to learn about advanced means and methods of construction, including robotics, industrialized construction, and the use of AI. I'm pleased to tell you that some of these very courageous Ukrainians are joining us today in this webinar. For Ukrainian construction to succeed, we know it must be Ukrainian-led, employing sustainable, efficient construction methods. This massive rebuilding effort, the largest since World War II, can reshape the design and construction industry, benefiting everyone around the globe. Ukrainians have exemplified innovation under duress over the last almost 2 years of this war. Let's respond to their darkest hours with the innovation and ingenuity that Americans can provide. We'll be providing information about ways you can get involved in the coming weeks. Please contact us via our website if you'd like to meet the group or volunteer to show them the very best of the San Francisco Bay Area in January. So now to today's webinar. Today, we're so pleased to host a conversation with Joe Callis. Before we introduce Joe, a word about our webinar protocols. We are recording this session and we'll place it on our website, centerforinnovation.org, in the coming days. Our webinars are also now available as podcasts, so you can check them out wherever you download your podcasts. We encourage your questions, so please use the chat box or Q&A, and we'll take them at the end of the presentation. Here's a little bit about Joe. He's an architect and a cultural heritage specialist currently working with UNESCO. A PhD candidate at Penn State University, his research focuses on combining AI and machine learning with 3D point clouds to expedite the structural assessment of historic buildings for enhanced disaster reconnaissance missions. There's a lot of complications in that sentence, but the wonderful thing you'll learn about Joe is he's going to break it down to make it understandable to everyone. Joe also conducts what is called feature importance analysis to identify attributes in unreinforced masonry buildings that increase vulnerability to blast loads, assisting engineers and heritage preservation experts in data-informed retrofits to bolster resilience against future disasters. While Joe's focus is disaster recovery, there are numerous applications for his research in documenting existing conditions in all spaces. My wonderful colleague, David Wessel from ARG here in San Francisco, would now like to say a few words. David, you want to take it away?
I will. Thanks, Margie. Joe's presentation today is about the repair and restoration of historic structures suffering catastrophic damage. And we are unfortunately seeing daily destruction in the Middle East and Eastern Europe. In Ukraine, it appears that there is a deliberate attempt to erase cultural heritage by destroying historic buildings and districts. But I would like to ask you today to consider what Joe has to share in a much larger context than that of only restoration. The technology that he will discuss is not only applicable to historic and cultural sites, but also to the general built environment of our cities that will be undergoing rapid transformation in the coming decades, as we each have been experiencing. Buildings are buildings no matter what the age or who designed them, and documenting them accurately for the purpose of modifications or additions is needed for any project, not just cultural heritage. According to Architecture 2030, quote, in addition to the unprecedented growth in the global building sector, nearly 2/3 of the building area that exists today will still exist in 2050. So existing buildings are here to stay. As our cities become more densely populated, repurposing of non-historic structures and urban infill projects will continue and increase. There will be more adaptive reuse of commercial buildings, factories, warehouses, military facilities, etc. And for new uses to be inserted into existing structures, for additions to structures, and for new buildings to be built within the boundaries of vacant urban spaces, the setting and conditions need to be cost effectively assessed and accurately recorded. And Joe will share with us techniques to do this. The information gathered by the technique Joe describes can then be used to generate base information for design, assessing structural integrity, as you'll see, as well as for estimating quantities of material for repair, modifications, or additions. This speeds the entire process. So these techniques can be one tool in developing a relatively quick assessment of a project cost, which is, of course, the critical factor in deciding if a project will move forward or not. So now I'm going to turn it over to Joe, and I'm sure you'll enjoy what he has to share with us.
Thank you, Marty and David, for those amazing introductions. Let me just start by sharing my screen. So, hi everyone. I'm thrilled to be invited by the Center for Innovation to share with you some of my experience in the field of disaster response and recovery. So today my focus is on the role of technology in disaster recovery with insights drawn from the Beirut 2020 explosion. So join me on a journey moving from the initial disaster to the recovery phase, where I'll highlight the pivotal role technology played in expediting our response efforts. So as you've probably noticed, disasters are happening more often these days, whether they are caused by nature, human actions, or just accidents. It's becoming more crucial for us to just pay attention and come up with effective strategies to mitigate and respond to a diverse range of emergencies. One of these incidents was the devastating accidental explosion in Beirut in 2020. It had a huge impact, causing serious damage to existing buildings and shaking the entire city. The powerful earthquake in Turkey and Syria in February of 2023 left numerous people homeless and caused severe damage to existing buildings as well as cultural heritage sites. The continuing conflict in Ukraine, which began in 2022, persists with no apparent resolution in sight, unfortunately, causing ongoing damage to cultural heritage and existing buildings across the country. And just recently, destructive fires swept through a significant part of Hawaii, leaving existing buildings and sites either completely wiped out or severely damaged. So in the face of these disasters, it's staggering to consider that assessments are still, most of the times, being conducted in the traditional manner, manually, let's say, with hundreds of inspectors risking their lives on site. Especially for disasters on a larger scale, sending experts door to door for assessment is time intensive, and time is really an important factor, particularly for existing buildings after disasters. This traditional approach must be reconsidered to implement timely actions and prevent further losses, especially as time goes on. Unfortunately, disasters are becoming more severe, more frequent, and more impactful. For today's presentation, my focus will be on a specific case study, the Beirut explosion. However, I want you to consider this as more than just an isolated case study. Rather, view it as an application example that can be similarly applied to any other disaster site happening now or in the future and anywhere in the world. So just to start with a quick context, so on August 4th, 2020, one of the largest accidental explosions ever recorded in history, not caused by a nuclear reaction, occurred in Beirut. This event transformed its historic neighborhood from a bustling and vibrant cultural hub into a landscape of shattered buildings, collapsed masonry walls, and scratched pitch roofs. So some of the staggering figures to underscore the impact: 218 lives tragically lost, 7,000 people injured, and 300,000 individuals displaced, and 77,000 apartments left in various states of damage. But before delving into the specifics of what transpired and the subsequent efforts, let's begin by pinpointing Beirut on the map. I'm aware that many of you, if not all of you, may not be familiar with the location of Beirut or even Lebanon. So Lebanon is a very small Mediterranean country situated on the eastern coast of the Mediterranean Sea. It covers a total area of just 4,000 square miles, and its largest city, as well as its capital, is Beirut. Beirut is a peninsula city surrounded by the Mediterranean Sea. This cosmopolitan metropolis has a rich history, having been occupied by 15 different civilizations throughout its existence. As a result, it boasts a wealth of cultural and archaeological treasures. Often affectionately referred to as the Paris of the Middle East, Beirut has embraced a significant European influence in its culture and architecture. This blend of Eastern and Western elements creates a captivating fusion that characterizes the city. In the years following the Civil War, Beirut underwent a significant transformation. Many of its historical human-scale buildings gave way to a multitude of skyscrapers and towers, all in the name of modernization. Now let's briefly explore the historical architectural timeline of Beirut, particularly since the second half of the 19th century. This will help you grasp the predominant architectural styles in the area. So prior to 1850, Beirut was a compact coastal town enclosed within its walls, characterized by modular houses and narrow streets, as illustrated in the picture on the left. Between 1850 and 1919, Beirut forged strong commercial and political connections with European imperial powers, notably France. This period saw the city's rapid development, driven by European interests in Lebanese silk and other export goods, ultimately transforming Beirut into a vital port and commercial hub. During this same period, what we now recognize as Beiruti architecture emerged and has since defined the architectural landscape of Beirut. It is characterized by central hall floor plan buildings, triple arches adorning their main facades, and the use of European materials. Also, as shown in the photos on the right, even the interior spaces featured highly decorated elements inspired by European aesthetics, further reflecting the influence of European design on the Beiruti architecture. So later, during the French Mandate era, Beirut entered a phase of modernization characterized by the dominance of Art Deco and modernist architectural styles. These structures also embraced the back then innovative use of reinforced concrete technology. Between 1944 and 1975, modernism became assimilated within the architectural culture of Beirut and its suburbs, which turned Beirut into the avant-garde modern capital of the Arab world back then. So the Civil War happened in Beirut between the 1975 and 1990. So after 1990, the first action of the post-Civil War government was to designate only few historic buildings for restoration, and unfortunately to raise the rest of the historic center in preparation for the new construction and modernization of Beirut. This clearing of the city center led to the loss of some of the city's most valuable 19th century architectural heritage, with only few that remained. Now that I've provided you with an overview of Beirut's architectural evolution, let's shift our focus to the location of the explosion. Here we have a 3D map top-down view of Beirut City. The explosion took place in the northern part of the city within the International Port of Beirut. More precisely, it occurred in one of the storages situated directly across the grain silos. The explosion was triggered by ammonium nitrate, a substance that has been responsible for numerous industrial and accidental explosions worldwide, mostly in the United States, actually. While the exact cause of the explosion remains somewhat unclear, various scientific reports suggest that the 2,700 tons of ammonium nitrate stored had been subjected to poor storage conditions, which may have contributed to the catastrophic event. Obviously, yet unfortunately, the explosion had a profound impact on the city and its historic neighborhoods. It left behind an enormous crater measuring 140 feet in width. The overpressure generated by the explosion extended for several kilometers from the epicenter, causing damage even in areas quite distant from the site of the explosion itself. As I mentioned earlier, a considerable number of existing masonry buildings, mostly dating from the second half of the 19th century, sustained severe damage. This included residential mansions, residential buildings, palaces, villas, churches, and even multiple local businesses, and so on. Now, let's delve into the role of technology in this context. Personally, as an architect and cultural heritage specialist with expertise in heritage digitization, I volunteered under the Directorate General of Antiquities in Lebanon and the Beirut Built Heritage Initiative to implement and lead an emergency digitization mission. And here, before I continue, I would like to express that while I focus on my mission today, addressing the role of technology and its impact on disaster recovery, it's important to acknowledge the tremendous work carried out by all the volunteers, including architects and engineers involved in the BBHR initiative. This initiative served as the crisis unit supporting the Lebanese Ministry of Culture and the Director General of Antiquities. It's through these collective efforts that Beirut is being rebuilt faster. If you are interested, you can visit the BBHR page on Facebook to learn about the incredible accomplishments achieved by all those amazing souls in a very short period. So I just wanted to emphasize that I wasn't the only volunteer out there. There were many others contributing to these efforts. So back to my presentation now. My primary aim was to digitize, for the first time in Beirut's history, all the damaged historic buildings. This initiative played a crucial role in expediting the assessment process for these buildings and accelerating the implementation of emergency interventions. Typically, after a disaster, there's a tendency to either overestimate the materials required to secure a building, incorporating extra safety margins that result in significant cost overruns, or to spend too much time on site before securing the building while trying to analyze its specific needs. This latter approach, though cost-effective, can jeopardize the stability of the building due to the prolonged exposure to risks. Here's where the emergency digitization mission made a difference. By swiftly providing detailed 3D models of buildings, engineers gained instant access to these models, enabling them to take sections, assess floor plans, and conduct geometry analysis remotely. So it helped save costs by avoiding excessively high safety margins and allowed for the rapid implementation of emergency support. In the following slides, I will elaborate further on the details of what I was doing and how this technological approach significantly contributed to our mission. So my mission involved several essential steps. Firstly, we initiated aerial data capture utilizing a DJI Phantom 4 Pro drone. This involved taking pictures of each building, following a predefined path around the structures. Next, we carried out terrestrial data capture to obtain the additional details from close range. This phase involved the use of the available Nikon D800 DSLR camera, which followed a specific path and pattern to capture these close-up details. Later, the data captured by both the drones and the digital handheld camera underwent separate processing using the Agisoft Metashape Professional Edition software. These separate datasets were then merged to create the final 3D models for each of the buildings. The Cloud Compare software played a major role in this process as well. Initially, it was employed to clean the point clouds of the models, preparing them for further refinement in Metashape to create textured models at the end. Furthermore, Cloud Compare facilitated rapid structural analysis, allowing us to identify any tilting or bulging walls in the damaged buildings and assess the structural integrity. Finally, what we achieved was exemplified in the final output, a comprehensive model featuring detailed point cloud data, a meshed model, and a highly detailed textured model. These outputs were readily available for use by engineers, enabling them to conduct a wide range of analysis and assessments with precision. Let me try to play this video here. So here's a 3D animation showcasing the 3D models of some highly at-risk building that we digitized. This animation provides a clear visual representation of the extent of damage to these buildings. So during the digitalization process, all the models were georeferenced. In some cases, I placed coded targets on the buildings before documenting them, and later I recorded 3D coordinates of these targets using a total station to ensure accurate georeferencing during the processing phase. However, in situations where approaching a building was too hazardous, I incorporated corners of surrounding buildings into the model. I also recorded the 3D coordinates of these reference points using the total station, allowing me to georeference the models effectively during the processing phase. So as I said, those are some of animation of some of the models. To provide you now with more specific details about the outputs, let's focus on two particular buildings as examples. We'll begin first with what is known as the blue building. So following the processing phase and generating the final model, I also extracted high detail scaled ortho photos of all the 4 elevations and a top view of the building. These ortho photos served as additional resources for architect restorers. It's worth noting that my documentation efforts extended beyond just the exterior of the buildings. I made sure to document the interiors as well whenever possible. This not only facilitated the quick generation of floor plans, but also further accelerated the assessment process. Another important aspect was documenting the buildings before any cleaning or sorting took place. This approach allowed me to capture the location of each architectural piece and its disposition after the explosion, which is crucial for analyzing the impact of the generated overpressure. As shown in the pictures, all architectural artifacts were documented. Even non-reusable elements could be replicated with precision, matching their original shape and form to replace damaged elements during the restoration process. This level of detail ensures that the authenticity of the buildings can be preserved during their restoration. The 3D models, elevations, section, and floor plans that were made available to engineers played an important role in accelerating the implementation of emergency shoring and bracing. As you can see in the pictures, this technology enabled engineers to work faster and more efficiently, ensuring the stabilization of the buildings in a timely manner. In addition to the previously mentioned outputs, I also extracted standalone models of the pitched roofs for each building. These roof models were made accessible to architects, engineers, and manufacturing companies. They were able to use the provided dimensions to manufacture tarpaulin sheets promptly. The goal was to install these sheets as quickly as possible to provide shelter and protect the historic buildings from their primary adversary, which is water infiltration. Given that the explosion occurred in August and Lebanon typically experiences irregular rainfall starting in early September, so acting swiftly was of high importance. The second example I'd like to showcase is the Sursok Palace, a 19th century residential palace. This building represents a higher class structure from the same era in Beirut and offers a glimpse into its distinct architectural details. As mentioned previously, I also extracted high detail ortho photos of all 4 elevations and the top view of the Sursok Palace. So these ortho photos were made available as additional resources for architect restorers and engineers. The level of detail captured in these 3D models was very important. It's evident that not only the significant damages were well documented, but also the smallest and finest cracks are highly perceptible. So this comprehensive level of detail is important for conducting a holistic analysis of the buildings, which ultimately leads to more informed decision-making and better outcomes. Moreover, it significantly aids in the preparation of restoration files for funding, not only for the emergency interventions, but also for the subsequent recovery phases. In addition to documenting the floor plans of these historic buildings, I also captured the highly decorated interiors. This included detailed documentation of the ceilings, as illustrated by the images showcasing the sophisticated ceiling design of the Sursok Palace. These documents are not only crucial for understanding the structural aspects, but also for preserving the invaluable decorative ceilings that will prove invaluable in later phases, particularly for the surface restoration package, providing restorers with a better understanding of the state of conservation and damage to these ornate ceilings. This emergency digitalization mission played an important role in conducting a preliminary quick structural analysis to highlight weak areas in the buildings. So the 3D point clouds were post-processed using the open source software Cloud Compare. In Cloud Compare, we automatically determined and measured the deviation of the walls from the elevations planes. As shown in the photo on the right, scalar fields classifications were applied to the elevations of the buildings, enabling the study and analysis of their physical behavior following the explosion. In the photo, you can observe the V-shaped deformation in red on the upper walls of the elevation. This information was essential in helping engineers pinpointing the exact zones requiring interventions or consolidation, thereby guiding their restoration efforts effectively. Furthermore, this approach proved valuable in uncovering potential damages that might not be visible to the naked eye. For example, when I applied the same methodology to the side elevation where the towers are located, the scalar field analysis initially showed coherent colors across the entire elevations, indicating no major deformation of the wall, as you can see on the colored scalar field on the left section of the photo. However, when I focused solely on the towers, if you take a look on the right section of the photo, the analysis revealed a gradual shift in colors from red at the top to greenish lower down, signifying that the towers are to a certain extent leaning. I want to clarify that I'm not attributing this leaning to the explosion, as slender towers historically tend to lean over time before stabilizing. However, it's important to highlight these findings to engineers so they can conduct on-site testing to determine whether the tilting is active or not, and then make interventions decisions accordingly. Furthermore, when examining the connections between the towers and the elevation, I observed the presence of cracks, which corroborated the leaning issue as shown in the lower pictures. So these findings underscore the importance of thorough analysis and testing to ensure the structural integrity and safety of these historic buildings. Just like any other building as well, all of these documents proved valuable in helping engineers gain a comprehensive understanding of the structures and the damages, which eventually helped them implement the structural reinforcement. So in total, and supported by the outcomes of the digitization mission, the Beirut Built Heritage Rescue efforts collaborated with the Director General of Antiquities to promptly and effectively implement structural reinforcement and shoring for 60 heritage buildings that were at high risk of collapse in the affected regions following the explosion. This rapid response played a vital role in safeguarding these historic structures from further damage and potential collapse. In addition to structural reinforcement, the BBHR experts also played an important role in securing timely sheltering for 90 heritage buildings in the affected areas, once again supported by the prompt outcomes of the digitization mission. This crucial step protected these historic structures from additional damage caused by potential rain, further ensuring their preservation and safeguarding their cultural value. After the explosion, the BBHR volunteering team was conducting assessments on site of the damaged buildings. However, there was a significant challenge. There was no single reliable updated plan of Beirut that included heritage buildings to facilitate the assessment process, unfortunately. So furthermore, there was a lack of digital documentation for the area and a shortage of detailed heritage-related geographic information system, or what we call GIS data. Although various institutions and universities had worked on GIS platforms for Beirut, there was limited focus on the heritage fabric of the city, and there had been no platform that consolidated this data. So during the assessment phase, information was scattered across separate sheets, Excel tables, Word documents, and so on. So recognizing the need for a more organized and digital approach, I took it upon myself to volunteer once again and create a comprehensive heritage-related GIS platform. This platform was based on the data collected by BHR and aimed to make this information accessible to the Director General of Antiquities. The objective was to enhance their ability to manage ongoing work on site and prepare for potential future disaster more efficiently. So we created an efficient and transparent system to transfer all the data collected on site into a GIS platform. This initiative has significantly improved our understanding of the heritage buildings in Beirut, including their levels of damage, the specific location of different types of damages, the condition of pitch roof, the social occupancy of these buildings, and the status of the building that have been shored, sheltered, that have started restoration and conservation work. Moreover, the data is regularly updated to include information about any challenges encountered or in certain plots or the completion of work on specific buildings. This comprehensive data set not only facilitates monitoring by the Directorate General of Antiquities, but also streamlines their follow-up processes. Importantly, it has the potential to support future planning efforts for the area, not only in response to the current disasters, but also for long-term preservation and management of Beirut's cultural heritage. So the emergency digitization mission not only sped up emergency interventions, as I just demonstrated, but it also played a crucial role in expediting the production of restoration files and tendering documents. This accelerated process facilitated swifter fund acquisition, enabling us to promptly initiate the restoration and reconstruction phase. This was particularly noteworthy in a country undergoing one of the world's worst economic crises, allowing us to start the process earlier than expected. Here's a before and after photo showcasing the remarkable transformation of the Blue Building, which has been restored to its former appearance and even improved with the introduction of retrofit reinforcements to enhance its overall resilience in the face of future disasters. However, the Blue Building was not an isolated case. Many historic buildings have undergone restoration over the past 3 years and continue to be restored, revitalizing the neighborhood, thanks to the collective efforts of the local community. Here's another example of a restored 19th century building and many other examples that I'm gonna quickly go through. But what truly matters in the end is that through the restoration of these houses and all the efforts that the local community is doing, buildings and clusters, we are not only bringing these historic structures back to life, but also revitalizing the neighborhood by welcoming back the residents who had to temporarily leave after the explosion. While much has been achieved, there is still a long road to complete recovery from this disaster and requires collective efforts. A 10-second explosion resulted in multi-year restoration, reconstruction, and rehabilitation works. This underscores the importance of proactive disaster planning and the creation of efficient disaster management plans. Such preparations can significantly reduce the impact of future disasters on historic buildings and communities, helping to safeguard our shared heritage for generations to come. And this is part of the focus of my current PhD research, in which I'm developing methods to automate the detection, assessment, and quantification of damage in historic masonry buildings located in post-disaster areas. The aim is to expedite reconnaissance missions and facilitate a quicker transition to the restoration and reconstruction phase. In reviewing the literature, it is evident that most studies concentrate on detecting a single type of damage, with a predominant focus on concrete, asphalt, and pavements for road rehabilitation or bridge inspection. In the realm of disaster-related studies, several have focused on utilizing this technique with satellite imagery to generally identify damaged and undamaged buildings post-disaster. While valuable for the rapid detection of affected areas, this method falls short in providing deeper insights into the quantification of damages or understanding the specific types of damage that may be more recurrent in certain buildings, making them more vulnerable and requiring more urgent interventions. And in fact, the problem of damage on historic buildings or any building or existing buildings in post-disaster areas goes way beyond the fact of generally classifying whether a building is damaged or not, or whether does we have cracks or not. It is often a very complex situation combining both structural and surface problems of different levels and types. So my goal at the end is to be able to reach a level of a holistic approach where I can automate a detailed damage detection on existing buildings following a disaster that takes into consideration all the aspects of damages that a building undergo during a disaster, rather than sticking to the usually researched types of damages. So as a first step toward my ultimate goal, I wanted to explore if I can automate the detection of large-scale damages. So I focused on detecting wall collapse damage first. Now, why wall collapse? Well, because it presents several challenges and complexity. So wall collapse lacks a specific or uniform shape, unlike cracks, for instance, and can occur partially or completely following the masonry joints or breaking through the masonry. On the other hand, detecting wall collapse damage is also complicated by the fact that it creates an opening into the building's interior, potentially making it harder for the algorithm to be trained on detecting it. So I wanted to conduct a proof of concept on a small data set just to see if it will work or not before moving to a more robust machine learning model. In this experiment, the methodology employed utilized the open source implementation of the mask RCNN method developed by Matterport, leveraging TensorFlow and Keras. Mask RCNN is a convolutional neural network designed for object instance segmentation, allowing precise identification of objects at the pixel level in images by predicting segmentation masks alongside bounding boxes. I won't delve into the intricate details to avoid overwhelming you with unnecessary information. In essence, so the process begins by selecting data or images for training our machine learning model, dividing them into two sets, the training set and the validation set. After constructing the data set, the next step involves labeling the images, given the supervised learning nature of this exercise. Subsequently, we initiate the training on the labeled data set, utilizing the validation set to assess the model's performance on unseen data, so we can know if our model worked or not. So briefly, those are some of the results. Our proof of concept experiment demonstrated that the method yields satisfactory results in detecting wall collapses on unseen images from Beirut explosion. And to test the transferability of our trained model, we conducted experiments on an unseen diverse set of wall collapse images from other disasters as well, that not just from Beirut, which were randomly downloaded from the internet. And our method also yielded good detection results in different disaster types, indicating its effectiveness in a real-world setting. So in my upcoming work, I aim to train a more robust machine learning model using 7,000 photos that are currently undergoing preparation and labeling. The goal is to enable the model to effectively segment various types, levels, and complexities of damage all at once. This effort aspires to automate a comprehensive assessment approach for existing building post-disaster areas. So with the existing of these amazing technologies that I mentioned and the promise of emerging ones to further accelerate disaster response and hopefully enhance disaster mitigation, several challenges arise as well. These include digital literacy, and as not all individuals, societies, and countries are familiar with or equipped to deal with digital technologies and platforms. Additionally, there are concerns related to data management and accessibility, questions about who should manage, select, organize, and disseminate the produced data, how to control big data, and understanding when to stop collecting additional data. Furthermore, the issue of the digital gap persists, contributing the unequal access of information technology. So in a world marked by inequalities and discrimination, can we truly ensure digital equality? I hope so. Thank you.
Joe, that was absolutely amazing. I'll share with the audience. I've had the honor of actually seeing this presentation before, so I can just imagine how many questions are going through your head as went through mine the first time that we saw it. I'm going to ask David Wessel if he has any comments. And then I'd like to encourage our audience to actually put questions in the chat box, and I will unmute you or reframe your questions as we go forward. So David, do you have any comments you'd like to make?
Well, I just hope everyone realizes the applicability of what Joe has presented today for the type of urban renewal that we're seeing. What comes to my mind is when we have abandoned buildings in cities and we're going to repurpose them, how important this type of work can be in terms of safety. So Joe, I understand that you were able to document all the interior spaces without putting anyone at risk. Am I right in that? Because you're using the drones to get into buildings, is that right?
Yeah, the drones, and in some cases, I was the only one entering. So, so yeah. But yeah, I was using my own experience as a heritage preservationist. So I'm a cultural health specialist that work with damaged historic buildings or restoring abandoned historic buildings. So I know where to step, how to step. But of course, there's always a risk. And we were always accompanied by the Lebanese army, who were usually assigning which buildings are that experts can enter and which buildings expert cannot enter at all. So we can, and in those cases, yeah, the drone was entering. Yeah.
Okay. Margie, I've got more questions, but I'd rather let our participants go first. So why don't you start there?
Great. We have a question here from, and please forgive me if I don't pronounce your name correctly, Sumani Goswami, asking how much time did the documentation of each building take? So, for example, the Blue House.
Yeah. So So let's say at the beginning of the mission, it used to take more time, but as we were going, through the days, it used to be faster. But let's say in average, yeah. So, but here it was an emergency mission, so we were just doing that. We were just documenting, processing, and then having outputs, and then documenting, processing, having outputs again, building after building. So usually. And it could have been faster because I didn't have computer stations that we were working on. I was just using my own personal laptop, so I had to find workarounds, use some Python scripts and stuff to try and accelerate some of the processing. But let's say data capture used to take for one buildings between 30 minutes to 1 hour as an average. Before it used to take more, and later it used to take less, but an average 30 minutes to 1 hour to take the photos of one building with the drones, and then another hour and a half with the handheld camera, let's say. So 2 hours, 3 hours per building for data capture, and running the processing of the model on my computer with the data pre-processing as well throughout the night. So it used to take 10 hours of pre-processing, but this was on my laptop, not on my computer station. On a computer station, it would have taken, a lot less time. So, yeah.
Great. We have a question here from Charlotte Matei. Again, my apologies if I've mispronounced your name. Asking, would you mind explaining again why the scans should be done before cleanup?
Sorry, what was the question?
The question was, would you mind explaining again why the scans should be done before any cleanup?
Oh, sure. Yeah. So as an architect and cultural health specialist, I'm also interested on, all the architectural features and heritage features that were, that fall on the, on the floor. So I as I showed in one of my slides, so I have all the architecture on wood features, stone features like stone corbels, stone decoration that fell, and so we can and sometimes we have a whole ceiling that fell, where we have the decoration of the ceilings, and the only resource to be able to recreate those ceilings during the restoration using the same design and same measurements is to have an accurate drawings of these. And the way to do this is to scan them before doing the sorting and before cleaning them out, and sometimes just throwing them into the dump. So I was insisting on getting everything as it was right after the explosion, because it also helps analyze later how each building behaved, so we can understand how the explosion reacted in different buildings and different parts of the city as well. Yeah.
Your answer reminds me, David Wessel and I and Dean Reed traveled to Kyiv this last summer for the work
Yeah.
that we were doing with Ukrainians about discussing reconstruction. And as part of that effort, we were together in Warsaw, and we walked through and saw the reconstruction of Warsaw. And talked with some people there. And one of the things that they told us is that they extensively used paintings, actually literally paintings in the museum, to understand what the historic core of Warsaw had looked like before it was completely flattened. And I mean, an entire area, the core of their historic city was literally rubble, no walls, nothing anywhere. So what did the streets look like? What did the walls look like? What was the height of the buildings? All of that needed to be reconstructed. And that was done through study of actual painting. So I have to say that I'm listening to Joe's presentation and trying to just understand that evolution of what we've been able to learn, and how technology has provided us so much more information about the restoration of buildings. So, so anyway, thank you for that, Joe. We have a question here from Dean Reed, a CFI board member, and he asks, are you currently working in Ukraine, and do you expect to work in Gaza?
Oh yeah, so I started working in Ukraine a year ago, around last January. And I went in Ukraine. I was there last May for 3 weeks and a half, where I was working on site. So, but mostly my current role involves collaborating remotely with organizations and experts to contribute to disaster response and heritage preservation efforts there. So, for instance, in the aftermath of the conflict in Ukraine, I collaborated with UNESCO on rapid damage and need assessments, leveraging my expertise in architecture and heritage preservation. And currently, we're doing the third rapid damage and need assessment now in December. Unfortunately, it's gonna still be done until the war stops. That we all hope it will stop soon. And yeah.
We have a question here from Mayank Patel. What software was used to identify deformations in the towers?
Okay, so I was using the open source software, which is called Cloud Compare. I can send the link in the chat. Actually, yeah. So the idea usually better, it's when you have a a model from the pre-disaster and then a model from the post-disaster. You can compare the both models and you can directly get the measurements in millimeter of the deformation of everything. But in our case, Beirut was not documented before, so I just had the models from after the disaster. So what I was doing, I was like defining a plane on each elevation, like from the elevation plane, and detecting the deformations of colorizing the let's say the model on by how much each point deviated from the elevation plane rather than from a pre-disaster model, which will be, of course, more efficient in other cases. And that's why I'm trying to always incite people and municipalities and governments to go ahead and document as much as you can your cities, because this will help not just after disaster, but help you mitigate for disaster. And if a disaster happened, you can better detect which building got damaged by just overlapping the previous model with the actual model and act in even faster way. Yeah.
Great. We have a question here from a great friend of CFI, Rex Donahue, who also participated in our innovation lab. So Rex's question is, should owners conduct data scans to collect benchmarking data for cloud compare studies as a form of insurance?
I mean, I'm always with letting everyone just collect point clouds, but yeah, it depends. We have to be aware who is collecting the data, how reliable is the data collected. There are some guidelines that needs to be followed, just that the model, the output model will be reliable enough to draw some, not just like for visualization, to be able to do some engineering work on it out of it at the end. Yeah.
We have a question here from Elian Buri. What is the accuracy of the end point cloud using the used photo imaging methods?
Yeah, so it depends. Each model, it depends on what was the case of each model. But I shared the barcode. I don't know if the QR code that I put in one of my slides was on the paper that I shared about the work done in Beirut, and it has a detailed one for 40 of those models. But in general, it varied between 3 to 7 millimeter, depending on each model. Again, depending on the scale of the building, on the scale of the monument, and yeah, depending on the defined GSD ground sampling distance of each building at the beginning of the documentation work. So it's a case by case, as that was not just like general, resolution, or let's say, yes, accuracy.
Great. We have a question here from Sumani Goswami. How would one
Mhm.
document a building which is surrounded by other buildings or debris, not
Oh,
clearly
yeah.
showing the facades? Great question.
Yeah, in Beirut, we had also electrical poles with wires. We had a lot of trees around the buildings and between the gardens. And yeah, so Beirut was an urban context, actually. So we had, yeah, and you have sometimes cars passing through the road. You have to ensure, like, you have to have a certain ensures a security, or maneuver in a way not to cause possible damage to anything. But yeah, so that's the point when you combine drone photogrammetry with handheld camera, like from ground photogrammetry. So you process models from different sides, and then you can easily remove, let's say, what is covered by the trees, or the wires for the drone cameras can be covered by the handheld camera, from the lower levels. And usually between the drone and the handheld camera, sometimes we use poles with cameras, like to have an intermediate distance as well, so we can cover more details when needed in certain critical areas. Yes.
Great. We have a question here from Muhammad Hassan. Can you tell me how you segment and detect the destructed parts of the buildings using 3D technology, in short?
In short, that cannot be done in short. But there's a lot of type of algorithms. There are a lot of packages that work on that. What the thing that I'm using was Mask RCNN. Actually, it's usually done to just detect objects, to detect people, faces. Those are technologies that are or objects. Those are object technologies that were developed for security cameras to detect people walking, or to detect certain things that people want to monitor. But actually, as you train them to detect a certain object, you train them to detect damages. So the idea actually is to start with a base data set that you have, and then you can try first to label the damage that you are looking forward to be able to detect eventually, and then train the computer on these data, and then assess its performance based on the test set that you pulled out at the beginning to test the how much the computer were able to detect on its own damages without looking at the data that it was trained on. And then yeah, the bigger the database that you have at the beginning, the better your model will be, and eventually you'll be able to detect it on whether images or 3D models. So there are algorithms that works on both, whether you want to detect on images and get pixel-based dimensions, or you can train a 3D model itself to be able to detect damages on as well. But this is very, very, very briefly. There's a lot of steps to do, of course. I can share links if you want of many papers on that are not specifically for damages, but are other objects that can be transferable for damages.
Maybe you could add to the chat box how people might contact you, Joe.
Yeah.
Just so let's make sure to do that, because I think there are many people from around the
Sure.
world
Yeah,
have much more detailed questions. So I'm just going to keep taking them till we sort of run out of time, if that sounds okay to everyone. We have a note here from Bahashik Abdallah saying thanks for the presentation. Is there any collaboration happening in Syria? Many damaged historical cities after the war and the earthquake really devastated Syria. He says, we could use your expertise, especially with low-cost methods. And then, so first the question about Syria, the second one being, what is the benefits of using Cloud Compare as part of this process?
Sure.
So two separate questions.
So for the first, sure. So for the first part, so I worked last February as well with UNESCO Beirut office, which is responsible for Syria as well, which operates for, which is a regional office that works for Syria as well. And we worked on the rapid damage and need assessment for after the earthquake disaster that happened. Unfortunately, it was devastating, especially after the war. Like many regions that were very heavy, like they were very rich in cultural heritage, were heavily damaged, not just from disaster, but from the war as well. And then you have a disaster over another one, and then things gets worse. So I know now UNESCO as well are trying to work more on conducting some capacity buildings on specific projects so far. But yeah, I guess I'll be up to do anything remotely if it can help you or a group of people, if you are willing to, do some core, like in NYU there to try and, document some buildings. This will help a lot, of course. And we could use, what is the benefit of using? Yes, the Cloud Compare. Yeah. Okay. So Cloud Compare, I use it in two ways. So the first way, it helps you better adjust the point cloud before moving to the textured mesh and meta shape. So you get better cleaning, better adjusting of, I mean, Cloud Compare is done just for point cloud. So it has a lot of flexibility when dealing with point cloud that you cannot find in usual photogrammetric software, which are great already. You might not need them, but just like for completeness, it's better to have more clean, let's say, point cloud first before moving to the mesh, which will result in a better meshed model and better textured model eventually. And then it was used to do the quick structural diagnosis and to detect which walls were tilting, where we have bulging, which towers are moving. Yeah.
Great. And then we have a question here from Mayank Patel. Again, my apologies if I mispronounced your name. We own a Matterport camera. Do you know if the masked RCNN feature is available to their users to analyze 3D models of buildings? Okay, super complicated question there.
Yeah. Okay, so we own a Matterport camera. Do you know if the masked RCNN feature is available to their users to analyze 3D models? Oh, but I'm not sure about the Matterport. So what I know about the Matterport, it's great for visualization, but I'm not sure about the measurements of it. So it's good for VR, for virtual reality. If you want to do virtual reality, video of your museum or house or anything you want to show, it's great. Measurements wise, I don't know much about it. So, and I don't know much about the outputs themselves to see if it's suitable, but we can look at it, sure. Yeah.
Great. Okay, so I'm gonna take my privilege as moderator to thank everyone for really terrific questions, from the very, very specific to the much broader. And I'm going to ask David Wessel if he'd like to say a few words, and then I will conclude our time together at the top of the hour. So, and that will also give Joe a little bit of time to put his contact information in the chat box for those of you who from around the world who'd like to follow up with him. But David, I just wonder if there's any last remarks you'd like to make.
Yeah, I have one quick question for Joe, and then I'll conclude. And that is, Joe, early when this technology was being developed, we used it for documenting existing buildings. And we had a couple projects where there were missteps, right? Didn't get the accuracy that we needed, or the detail, or what the client was expecting was different from what we provided. So I'm wondering if any bodies such as ASTM have started to develop standards for this type of documentation, for either the scanning, the point clouds, or anything else. Is that taking place yet?
Yeah, of course. There are a lot of organizations that are working collectively and sometimes separately to provide guidelines for both photogrammetry and laser scanning. So guidelines for both. And actually, there's the CIPA Heritage Documentation, which is an international scientific committee for ICOMOS, which is Comité International de la Photogrammetrie Architecturale, which is a scientific committee that was created by ICOMOS and ISPRS back in the 60s. And it deals just with generating guidelines and training people into how to better document sites and heritage, but as well, those can be replicated to buildings as well, not just like heritage buildings. We have the ISPRS, International ISPRS and ASPRS as well, International Society for Photogrammetry and Remote Sensing, and American Society for Photogrammetry and Remote Sensing as well. They have also on their website a lot of recommendation guidelines for both photogrammetry and laser scanning and what needs to be done to have a good output at the end. And currently, ECOMOS is also updating their new guidelines on how to document sites and cultural heritage buildings as well. That should be released next year, I guess. So yeah,
Right.
I can share links as well.
Yeah, that would be great. Well, I think I suspect that we have quite a large audience of individuals involved in cultural resources, but I hope those that are not have been able to see the applicability of the technology that Joe has shared with us today to all the type of building that will be involved in more and more in the future in the urban core. It's a tremendous technology to be able to get information quickly and develop cost estimates, quantities, et cetera, for those type of projects. And I'm sure it's going to be in much wider use in the future. So I'll turn it back to Margie.
Sorry. Thanks, David. Joe, from the bottom of our hearts at the Center for Innovation, I really want to thank you for all of your work. The marriage of your technical expertise, curiosity about how to do it, and commitment to preserving heritage and memory for communities around the world is just so inspiring to all of us. I really want to say that on behalf of all of the participants on today's call, and all of the people who will wander around these renovated cities over time. Cities which have been destroyed due to war, destruction, climate change, and all the other things which are happening on our planet right now, and wander in awe of places that they might not have been able to explore or understand had it not been for the technological resources you bring to your work. It's really just amazing and so inspiring, not only for all of us today, but also for our children going forward. So really, thank you so much for that work. Joe's going to put his contact information in the chat box if he hasn't already. I haven't checked. I would like to just end our time together with the group by saying that this is the last public webinar for the Center for Innovation of 2023. You can join us on January 12th for a webinar highlighting the research and solutions created through our Innovation Lab program. That's real innovation strategies used in real workplaces all around the world. And so the participants of the lab are going to share what the problems were and their solutions. It's always incredibly inspiring with lots of really great solutions which are shared by people about changes they made in their companies, which you might consider using within your own practices. If you're interested in learning more about the Center for Innovation's work with the Ukrainians who are coming to San Francisco in January, please feel free to reach out to me through the Center for Innovation website, centerforinnovation.org. We are recording today's session. It's going to be placed on our website in the coming days. You can also listen to them on podcasts, so you can check it out wherever you get your podcasts. I'd like to thank April Willoughby for all of her behind-the-scenes work of making all the technical information magic happen for us. She's really the glue that keeps us all together. If you aren't yet a member of the Center for Innovation community, please be sure to subscribe to our newsletter and also receive notification about our webinars. We do 1 to 3 webinars a month, depending upon the capacity of our staff and our wonderful community who gives us their time and energy at doing their work. Finally, thank you to our sponsors and to you, our community of innovators around the world, for making the changes we know which need to happen to create a better world for everyone. Have a wonderful holiday season and a peaceful new year, and we'll see you in 2024. Thank you for your time.